This video is about motion diagrams, which are tools to describe the motion of an object over time, specifically position, velocity, and acceleration. So as an example, let's create the motion diagrams for a car. The car is initially stopped at a stoplight and then accelerates down the road and then comes to a stop again at the next stoplight. Let's say the trip is broken into 3 segments. In the first segment, the car accelerates with a constant acceleration. In the second segment, the car travels at a constant speed. And in the third segment, the car slows to a stop, again with constant acceleration. Let's get a general idea what's happening with position, velocity, and acceleration before we draw the plots. So here are the 3 segments. Let's start by getting a general idea about position. Let's go ahead and add the coordinate grid to the picture up here so we know which direction is the positive x direction. Well, pretty clearly the car is getting further and further in the x direction. So in each zone, it's increasing. So that one was pretty straightforward. Let's look at velocity. So in the first zone, the velocity starts at 0 and increases to a maximum value. In the second zone, the velocity is constant. It stays at that maximum value. And then in the third zone, the velocity decreases back to 0. Now let's look at acceleration. In the first zone, the car's acceleration is to the right, so that's in the positive x direction. In the second zone, the speed isn't changing, so the acceleration must be 0. And in the third zone, the car is slowing down, so the acceleration is opposite the velocity or in the negative x direction. Okay, now let's try to draw the plots. So here are the 3 sets of axes for the position plot, the velocity plot, and the acceleration plot. Notice the horizontal axis for each one is time. You might also wonder why I've drawn the acceleration one a little bit differently, and that's simply because I know for this scenario that there are positive and negative values of acceleration for the car, and there weren't positive and negative values for position and velocity for this scenario. In general, there can be positive and negative values for any of the plots. Okay, let's break up these plots into 3 time zones. So these zones correspond with the 3 position zones we drew in the previous diagram. So let's draw the 3 plots. It's often easiest to start with the acceleration plot. So let's do that. We know that in the first zone, the acceleration is constant and it's in the positive x direction. So it's a positive constant value. In the second zone, we know that the car is moving with a constant speed, and acceleration is equal to a change in velocity over a change in time. So if the velocity is constant, if it's not changing, then the acceleration must be 0. In the third zone, it's constant again, but we're told the acceleration is in the negative x direction. So it's a negative constant value. So now let's try the velocity plot. A useful technique when doing these plots is to mark key points and then connect those marks or connect the dots. So we know that the car's velocity in the beginning is 0, so let's mark that spot. And we know at the end of this first zone, the car reaches a maximum speed or a maximum velocity. So let's mark that spot. So now we want to connect the dots. And the question is it connected with a straight line? Are these 2 dots connected with a curve like that or a curve down like that? Get the answer by thinking of the acceleration. In the first zone, the car's acceleration is constant, so the change in the velocity is constant. In other words, the car speeds up by the same amount every second. That produces a straight line mathematically. In the second zone, the acceleration is 0, so the velocity isn't changing, or in other words, it stays at that Vmax value. In the third zone, we can mark another key point. We know that at the end, the velocity has gone to 0 again, so we want to connect the dots again. Just like in the first zone, the acceleration is constant, so we know that we're going to connect these two dots with a straight line. Now for the position plot. This is often the more difficult of the three plots. Let's mark two key points first. We know that the car starts at x equals 0, and then at the end it's reached some maximum distance, some maximum x value. So the game now is to connect the dots. How are they connected? So that's the challenge. Let's start with zone 1. Just as we used acceleration to determine the velocity curve, let's use velocity to determine the position curve. So in zone 1, the velocity increases. So logically what that means is the car is knocking out bigger and bigger chunks of distance every second. That would produce a curve like this. In zone 2, the velocity is constant. So the car knocks out even chunks or the same chunks of distance every second. So that's a straight line like this. We know that the straight line curves up because the car is getting further and further away. X is increasing. In zone 3, it's a little bit like zone 1. The car knocks out, because the velocity is decreasing this time though, the car knocks out smaller and smaller chunks of distance per second, and that produces this curve. So there are the three motion plots for the car scenario. Granted, it wasn't very obvious, especially for the position plot. But what I want to do next is give you two rules that relate these curves to each other, which should help you to create these curves for other scenarios. And then I'm going to show you that there's a pattern to these curves, which should also help you to double check your work and make sure you've drawn the curves correctly. The rules come from our equations for average velocity and average acceleration. Consider a standard XY coordinate grid. For any curve or line on this coordinate grid, you probably know that the slope is rise over run, or in this case, delta y over delta x. For our velocity plot, the vertical axis is v, and the horizontal axis is time, t. So that means that rise over run with a slope is delta v over delta t. Notice that delta v over delta t is not only the slope, but it's also the average acceleration. So based on that relationship, we know that the slope in this plot is equal to the acceleration. We come up with our first rule. The slope in the VT plot is equal to the value of the acceleration in the acceleration plot. So let's go through a similar analysis with the position plot and we'll get our second rule. If this is the position plot, then the slope of this line is delta x over delta t. From our equation above, we know that delta x over delta t is also average velocity. So that gives us our second rule. The slope in the xt plot is equal to the value of the velocity in the velocity plot or the VT plot. All right, so now let's see if we can apply these rules to the motion plots for the car that we had previously come up with. So here's our first rule, a little bit abbreviated. Acceleration is equal to the slope in the VT plot. Let's consider a point here in the VT plot. Say the slope of this point is 4 meters per second squared. That means that down here at the same instant in time, the acceleration must also be 4 meters per second squared. Or pick a new point. Say the slope here, what we can tell, since that's a straight line, it's also going to be 4 meters per second squared. So down here, the acceleration must also be 4 meters per second squared. And so that explains why the acceleration needs to be a constant value as the velocity has a constant slope. Let's pick a new point. So right here, what's the slope there? It's 0 meters per second. So down here, the acceleration must be 0. And over here, the slope is now a negative value. So when the line is down below the horizontal like this, that is a negative slope. That means the acceleration must be that same negative value, negative 4 meters per second squared. Okay, so that's how you apply the first rule. Let's apply the second rule, which is velocity equals the slope in the xt plot. So the value of the velocity is equal to the slope in the xt plot. So let's consider this point. The slope there is, say, 2 meters per second. So that means down here, the value of the velocity must be 2 meters per second. Let's pick a new spot here. That's a little bit larger slope. Let's say that's 3 meters per second. So that means here, the value of the velocity is also 3 meters per second. And right here, it's a larger slope, say 4 meters per second. So that means down here, the value of velocity is 4 meters per second. This spot here, it's a slightly larger slope. Let's say it's 5 meters per second. So this value is 5. And then right here, it's along that constant slope. So that means the velocity is still going to be 5. So we have a constant value of velocity as well. Now over here, the slope has started to decrease. It's still a positive slope. Let's say it's now 3 meters per second. So down here, it's still a positive number, but it's a smaller number. So now we're starting to go back down. Okay, so that's how we can apply these rules. I have one more useful piece of information to give you. Because these motion plots can be tricky, I think it's useful to recognize that there's a pattern to the curves, which actually comes from the two rules we just discussed. I'll show you these patterns in 4 scenarios. So here in the first one, let's assume we have a scenario with a positive constant acceleration. That produces a positive slope, constant slope for the velocity, and then that produces a curve in the position plot that curves up like this. Now, one thing to point out here is you might be dealing with a scenario that only deals with part of these 3 curves I've just drawn. In other words, zone 1 for our car only dealt with this part of the curves. Or you might have a scenario that only deals with this part of the curves, and so on. So just be aware of that. The pattern I'm showing you is the larger curve, and you might have a scenario dealing with a piece of the curve. Okay, in the next scenario, let's put the acceleration down here. It's now a constant negative value, which gives us a negative slope for the velocity. Excuse me. And that gives us a position curve that looks upside down like this. Again, you might be dealing with an aspect of these 3 curves. And then the next one is a 0 acceleration. Now the 0 acceleration actually gets broken up into 2 scenarios. So let me draw it twice. One scenario, if we have 0 acceleration, that means we have a constant velocity. But that could be a constant positive velocity or a constant negative velocity. And then that affects the next curve, the position curve. If it's a constant positive velocity, then that gives us a positive slope, positive constant slope in our position curve. And then the negative velocity gives us a constant negative slope for the position plot. Okay, so that's it. Those are the that's the pattern to the curves you might see. So that's it for motion plots. Next up are the kinematic equations that then put these variables that we've been discussing into use.